The engine can be split up into four main areas: compressor, combustor, the turbine, and the exhaust. The compressor has two jobs. It sucks and squeezes, drawing air in from outside, and also compressing the air. Some of the air is forced into the combustion chamber at very high pressures, so that when fuel is mixed with it and ignited, a rapid increase in heat energy is produced. The combustion chamber is where the bang happens. The burning mixture of air and fuel is sent rushing at high speed into the turbine. As this gas expands, part of the energy is used to power the turbines, which in turn drive the compressor. Finally, the gas is blown out through the exhaust nozzle. It has lost some of its energy through the turbine, but has enough left over to accelerate through the nozzle, providing a fast-moving propelling jet stream out of the back of the engine, and therefore, by reaction, creating an equal and opposite forward thrust. This is the whole point of the operation, taking air in at normal speed and forcing it out at a higher speed, backwards, thus sending the engine forwards. It may sound absurd, but it really is very simple. And it works. It is important to remember that these individual stages form a complete and continuous working cycle, a constant generation of power. And here are both the advantages and disadvantages of the way in which a jet engine works. On the one hand, the jet engine has relatively few moving parts, and as it's a very effective method of producing power, it can be small and light for a given output. On the other hand, the components at the hot end of the engine have to be able to withstand tremendous and continuous operating pressures and temperatures. All the sections of the engine are designed to make the flow of air through the engine as efficient as possible. The compressor does this by having both rotating and stationary blades, or rotor and stator blades. The rotor blades take the air and force it backwards through the engine, while the stator blades channel the air so that it hits the next series of rotor blades at the right angle. As the air is pushed through the compressor, the space available for it is reduced, and it gets literally packed in, so much so that compression ratios of up to 40:1 are possible. The compressor is driven by the turbine. One turbine can drive the whole compressor, but now there are often 2 or 3 turbines in an engine, each with a separate shaft that rotates a different section of the compressor. The fact that the sections can then rotate at different speeds means it is easier to maintain the correct overall flow of air through the engine, and the entire engine can be made shorter and stiffer. When the air reaches the combustion chamber, it's at a pressure approaching 600 psi, and it's travelling at more than half the speed of sound. Fuel is difficult to burn under these conditions, so a combustion chamber provides the correct environment, an area of more slowly moving and swirling air that is sprayed with fuel. This mixture will ignite, and the increase in heat energy is quite considerable. The burning gas can be as hot as 2,100 degrees centigrade, and at this sort of temperature, the metal the turbine blades are made of will melt. However, cooler air continues to be mixed with the burning gas to lower its temperature before entry into the turbine. And more cool air that had not been taken through the combustion chamber but diverted for cooling purposes brings the operating temperature of the turbine blade down to a more manageable 1,000 degrees or so. In some ways, the turbine is the compressor in reverse. Nozzle guide vanes channel the gas onto the turbine blades, which are shaped so that the gas flowing over them is used to generate the optimum power. The blades are slotted onto a disc which rotates the shaft that is connected forwards to the compressor. Often, as well as driving the compressor, the turbine will also provide ancillary power to even drive a propeller. It is vital that turbines are perfectly designed and manufactured. Just this one stage, the high-pressure turbine can generate up to 70,000 horsepower, at which point the blades will be spinning at 1,500 feet per second. That's over 1,000 miles per hour. So everything must be done to ensure that the passage of gas through the turbines is as smooth as possible. Similar care is taken as the gas leaves the engine through the propelling nozzle. It is these exhaust gases that provide the thrust to power the engine, so essential that they are propelled from the engine at exactly the right speed required by the aircraft. This is largely determined by the size and shape of the propelling nozzle that can give a kick to the gases as they leave the engine. The completed engine is, of course, a rather more complex affair, once the noise suppression, pollution reduction, cooling, lubrication, electrical, fuel and other systems have all been added. But the 4 sections of the working cycle remain unaltered. Soon after the invention of the jet engine, it was decided that brute force alone wasn't enough, and designers started to look for ways to develop this newfound source of power. The type of engine that we've been looking at is called the turbojet. It was the first kind of jet to be made, and it remains the best for high-speed flight, as it's very powerful but small and has a low frontal area, so it can be easily streamlined. The turbojet can be made even more powerful by adding reheat. In this system, fuel is sprayed into the exhaust and lit, so there is a second combustion stage which provides extra thrust. Reheat is generally used only for short periods to give extra acceleration, such as on takeoff or maximum climb. On landing, however, deceleration is wanted, and then thrust reversers are used. These are flaps that move to divert the gas forwards rather than backwards through the exhaust. This has the effect of slowing the aircraft down, as the jet reaction tries to propel the engine in the opposite direction to the airflow. A development of the turbojet is the turboprop. This has an extra turbine which, through a gearbox, drives a propeller. Aircraft powered by a turboprop are not as fast as those powered by a turbojet, but nevertheless, the turboprop remains a very efficient and economical engine. If the propeller is removed from a turboprop, then the resulting engine is called a turboshaft. The shaft is coupled to a gearbox, and through this it can drive a helicopter rotor. Much of the latest development, however, has been done on the turbofan. Here, only some of the air is fed through all the compressors, the combustor and the turbines. The rest is partially compressed and is bypassed around the hot core of the engine. This cuts down the engine noise as it reduces the overall speed of the exhaust jet stream. It also makes the engine very economical, since it's aerodynamically more efficient to have a lot of air moving relatively slowly rather than a little air moving relatively quickly. At very high speeds, to provide the thrust needed, it is necessary to have a small amount of air moving more rapidly. This is why the turbojet is used for supersonic and high bypass ratio turbofan for subsonic aircraft.